Gentlemen, can you put your hands together for Maksim?
Hello, DEFCON. How are you doing? Nice. I had a party near my room all the night, so I slept like 45 minutes. So I'm sorry if my brain will switch off at some point of this presentation, but hope we'll manage to do it. So we're going to talk about zero bugs found, hold my beer AFL, how to improve coverage-guided fuzzing and find new 0 days in tough targets. So glad to see all of you here. First of all, let me thank DEFCON Goons for having me here. I'm really excited to speak at this stage today. Before we actually start, let me introduce myself. So my name is Max. I have spoken at various security conferences around the planet, mostly about dynamic analysis of machine code. And last year I presented at DEFCON a talk about malware fuzzing, so check it out if you're interested in this topic. I have experience working on open source fuzzers such as WinAFL, DRAFL, contributing in open source framework DynamoRio, and working on implementing extremely abstract operating system for Windows malware analysis at IBM Research in Israel. So currently I'm working at Salesforce Red Team as an offensive researcher, searching for 0-day bugs, writing exploits, and doing engagements. In my case, I need to identify vulnerability and write exploit in a very, very short period of time. And that's actually where our story about efficient coverage-guided fuzzing begins. So we are going to talk about fuzzing today, right? And what kind of problems we face when we use AFL. I will describe what coverage-guided fuzzing is and explain how AFL actually works. Then we're going to talk about downsides of AFL and how each of them can ruin your entire fuzzing campaign. And in the second part of my talk, I'll present a new coverage-guided fuzzer implemented in pure Python that's supposed to address all of these problems. And of course, we will compare it with AFL. I will show you a couple of vulnerabilities I managed to find with this fuzzer. And so what is fuzzing? And more importantly, what is coverage-guided fuzzing? So the general idea of fuzzing is actually a dream of any professional procrastinator, right? So you run a special tool. This tool mutates your input, provides this input into your target, and you just see it, wait for a crash. That's basically all. Let's see it on example. Let's say we have a very trivial program that crash on input pound it. We start string 5As. We cover first couple of lines, program exits, we do it again and again until we find something that can cause a crash in the target. In this example, our fuzzer needs to mutate the string from 5As to pound it. And this is very unlikely and can take hours or even days to finally find this null pointer dereference. So to be able to address this problem, people invented coverage-guided fuzzing. People also call it feedback-driven or smart fuzzing. In this case, we continue mutating our input, but at the same time, we estimate coverage triggered in our target. So if we see that our input lead to some new path in the target, we save this input and then perform a subsequent mutation on top of this input. We do it again and again, we apply the same algorithm for the next finding, we save it, we mutate the next byte, search for potential new path opened by this mutation, then save it again, mutate the next byte until we finally find an input that can trigger a crash in our target. So this way we can cover the program in depth, and actually it dramatically increases efficiency of your fuzzing campaign. So instead of spending hours or even days doing blind fuzzing, you would be able to find this null pointer dereference just in a couple of seconds. So you see the difference. And this algorithm is the basis of the most known today coverage-guided fuzzer called American Fuzzy Lop or AFL. So AFL was created by Michal Zalewski 5 years ago, and today it's a standard de facto coverage-guided fuzzer for bugs hunting. It's attracting people with its efficiency and successful stories of critical vulnerabilities found with it. And it's a very powerful solution for vulnerability research, especially if you have source code of your target. So I have prepared a short visualization of how AFL actually works. So here on the screen we have 4 windows. In the left upper window we can see AFL status screen. It's just regular AFL status screen. In the right screen we see number of files already exist in our queue. So as soon as we continue mutating, we increase in our files, number of our files in the queue. So in the left middle window we can see content of file, of actual file that we are going to provide in our application. And it's in hex. And I'm indicating with red the actual change that AFL performing on our input. So you can see it perform a lot of random mutations in our file. And as soon as we continue mutating this input, the number of paths is growing. You can see it on the plot on the top, on the bottom left plot with white background. So you can see it's growing. And in this example, we do fuzzing against 7-zip. It's just, let's stop this video and move forward. So for the past 5 years, AFL proved itself to be a very efficient fuzzer to find memory corruption bugs in many different projects on many different platforms, both in user land and in the kernel of all widely spread platforms. There is even kernel version of AFL called KFL. I managed to find a couple of bugs with this tool, but this is a different story. People even search for bugs in very specific places like SCADA systems, switches, wireless hardware, medical devices, where any problem with software quality, security can cause serious consequences or human lives. So while many of you might think like, okay, Max, memory corruption bugs are cool, but we are running in the cloud, right? Well, this is true. C and C++ remains to be on the top of the most used programming languages. So our world is running on top of C or C++, fortunately or unfortunately. We can also look into statistics on number of research publications about fuzzing year by year, and we can definitely see the trend. So it's growing, and last year it exceeded 1,500 publications. It's a very hot research topic today. A lot of people play with fuzzing, and a lot of companies invest in this technology. Google even has an OSS-Fuzz project where they integrated fuzzing within software development lifecycle of 160 open source projects. They use a lot of CPU power, and they already identified 1,000 memory corruption issues by generating 500 billion test cases per week. So this high popularity of fuzzing across security community means that it's becoming harder and harder to find new bugs in products and libraries already covered by security researchers or projects like OSS-Fuzz, right? So we have to search for some new strategy and be able to perform fuzzing more efficiently than other tools. And to be able to perform fuzzing more efficiently, we have to understand what kind of issues already exist in modern fuzzers and be able to address them. So let's start with the first one, and it's a volatile path. What is volatile path? Let's say we have input 8 A's that cover these 3 branches in our target, indicated by green. We mutate 1 bit, and now it covers 3 previous branches and 2 more, shown in yellow. So if we, just a second. Okay. So if we send this input again in the target, it again covers only the first 3 paths. So we send absolutely the same input in our target, but now it doesn't cover path indicated by yellow. And those paths considered to be volatile. They do not depend on input, but parasitically executed in our program due to some randomness. And it happens pretty often, especially if we work with multi-threaded application. And our fuzzer actually has a dilemma, what to do with this input. From one point of view, it can just run it multiple times, right, and then reject it if it sees some path appears and disappears after each run. But what if we actually discover something new with this test case? In this situation, we would reject a new finding. Okay, we can keep test case and raise a warning for our user. That's what we actually have in AFL. But in this case, if our target is very volatile, we can end up with a very large corpus that actually do not cover anything new at all. So we would just wasting our fuzzer time. Second problem is parallelization. Let's say you have a really slow target and you don't know how or don't know how and don't want to actually spend time on increasing performance of your target, right? So you are not a performance engineer, you are a security engineer. So AFL wasn't designed to be parallel from the beginning. Of course, there is functionality that allow you to create master and slave instances, but let's discuss how it actually works. Let's say we have one master instance and two slaves, along with 3 files in our corpus. AFL can perform deterministic mutation on master instance and random tweaks on slaves. So the corpus will be copied into each instance, and all of the instances will perform mutations in each file one by one. If one slave finds something new, this file will be distributed to other instances, and they will continue mutating this, the same finding. So that's all actually what we have in terms of parallelization in AFL. It will work fine for fast target and when we have small corpus, but it will perform much poorly on slow targets, especially if we have a really large corpus. So there is no easy way to distribute this corpus between instances and ask AFL to share code coverage in a smart way between them. And I believe we can parallelize better here, and I'll show how a little bit later. Another problem is the lack of network fuzzing mode in AFL at all. So we actually don't have much fuzzers that can perform network fuzzing, coverage-guided network fuzzing at all, especially on Mac. On Linux, we can try some AFL forks or honk fuzz. On Windows, there is network fuzzing mode implemented by me last year, and we can try honk fuzz on Mac. That's actually all. Usually when you want to fuzz network application, the general advice is to somehow make your application to receive input over file instead of actually doing fuzzing by sending network traffic, right? But it significantly reduces number of potential applications where we can use this approach, especially if we deal with black box binaries, when we don't have source code and we can't just modify our target. Speaking about other platforms such as Windows, we are significantly limited in number of potential tools we can use. Basically, if we don't have source code, there is WinAFL, and if we have source code and our target can be compiled with Clang, we can apply libfuzzer, which is basically designed to perform fuzzing of library API calls. And that's all. All of these tools have their own limitation, of course. On OS X, we have even less tools that we can use to fuzz userland application. Basically, we can try to compile our targets with Clang and use libfuzzer if we have source code. If not, there is actually nothing that can perform coverage-guided fuzzing for you. Well, at least I don't know about this. And of course, I am not the first one who wants to address these problems. There are a lot of researchers who try to address these issues and improve AFL in some way, such as AFL Fast, AFL Smart, WinAFL, libfuzzer, honkfuzz, and many, many other tools. There are a lot of effort to leverage coverage-guided fuzzing on kernel, such as syscaller that demonstrate incredible results, along with KFL, 3/4, and others. I just listed some of projects here and papers published in the last year. So we can dedicate entire day describing different fuzzing solutions and techniques. And there is a nice paper where you can find a systematic research on all existing fuzzers if you want to go deeper in this topic. And I apologize if I forget to include some research or tool here. It's not because this tool is not great, it's just because we have limited amount of space here and of course time. However, if we summarize all of our requirements and problems that I described earlier, we can see there is a huge demand for a new fuzzer here. This fuzzer should be very flexible in terms of scalability, parallelization, and platform dependencies. And at the same time, it should be able to address volatile path problem and be able to support data mutation with multiple fuzzing strategies in one fuzzing campaign. Of course, this fuzzer should also support functionalities that already exist in modern fuzzers, such as allowing user to provide custom mutation algorithm to be able to implement specific fuzzing strategies, or even enable structure-aware fuzzing, which is a very, very promising technique today. So, ladies and gentlemen, let me introduce Manul, a new coverage-guided fuzzer implemented in pure Python that tries to address all of these issues I presented on the previous part of my talk. Manul was born to be parallel from the beginning. It can obtain coverage from FL instrumented binary or from DBI frameworks like Intel Pin or DynamoRio. I'm trying to support Linux, Windows, and there is a beta version support for Mac. I decided to call it Manul after the most fluffiest cat on the planet. Basically, in English it's called Palace cat, but in Latin it's called Atacalobus Manul. So Manul is very adaptable cat, capable to live and hunt in very severe weather conditions of Central Asia. And I just like this cat. This is actually second DEF CON talk where I present exactly the same slide. And this template was actually made out of this picture. So I process it through neural network and then just apply black color. Okay, moving forward. Let's talk about architecture. Of course, Manul employs module-based design. You have network module, instrumentation, modules core, UI, mutators implemented as plugins. This way, user can ask Manul to enable or disable different mutators, or even provide his or her own and ask Manul to use them. If we want to understand how Manul address volatile path problem, it's pretty straightforward. Let's say we have two volatile paths indicated by yellow. When Manul sees that our input covers something new in the target, we will run this input a couple of times. It's called calibration in coverage-guided fuzzing. And then just if we see some randomness in our coverage, some random paths, it will temporarily blacklist those paths and ignore them in the next runs. So first time I found this algorithm in KFL kernel fuzzer, and I just decided to integrate it with Manul. Probably it was introduced in some other fuzzer, but I first found it in KFL. Okay, moving forward. Parallel fuzzing is default feature in Manul. You just need to specify how many fuzzing instances you want to spin up using the command line argument. So Manul will automatically start all of them and split the corpus equally to each instance. So in this case, each instance will have only small part of the corpus. So we will have only, this way we can smartly distribute our corpus across instances. And we can even spin up a remote instance on some other machine available over network. So Manul will be able to share corpus and coverage with this remote instance like it's running on the same machine. This way you can like have your own like fuzzers cluster on top of Manul. And basically each instance is an independent Python process that utilizes its own shared memory. At the same time, Manul main process will be able to synchronize coverage and share it across other instances to avoid double work for them. So if one instance found some new path in the target, all other instances will at some point know about that and will focus on something else. So in this way we can smartly distribute our fuzzing campaign across all available cores. User can easily provide a third-party mutator via plugins. So it's only required to place your plugin in a special folder where Manul main binary located, and plugins can be implemented in Python and should contain init and mutate functions. So far, I have implemented two fuzzing strategies by default, so you already have it in Manul. The first one is AFL strategy, ported from C to Python, and the second one is Radamsa, distributed as native library. Network fuzzing is an experimental feature. So you can try to fuzz TCP or UDP server, it works. And you can ask Manul to act as a TCP or UDP server to fuzz some network client. But this feature in very beta stage, so expect problems. And black box binaries fuzzing is a very important part of Manul. So by default, Manul supplied with 2 DBI clients for Intel Pin and DynamoRio. Manul will start binary using one of these frameworks, so you can choose what you want to use, DynamoRio or Intel Pin. Then DynamoRio or Pin launcher will start your target, inject instrumentation library. Instrumentation library will open shared memory and will check coverage back to Manul. So pretty straightforward way. And I recommend to use DynamoRio because Pin is only supported on Linux and it's slow. So this is how it looks when you run it on Windows. Manul will launch a lot of Python processes. Each of them will run DynamoRio. DynamoRio launcher will run the target and with injected instrumentation library. And then instrumentation library will provide coverage back to Python process. So pretty straightforward. This is interface. We have information about volatile bytes, coverage, number of iterations, crash, exceptions, and many other useful things. And it also has its own logo implemented as ASCII2 art, so just to have logo. Each tool should have logo. So Manul supports 7 most used options via command line and dozens of others that should be provided via configuration. So in this way you can adjust Manul for your own purposes. And let's see it in action. So this is Manul main folder with a lot of files for different platforms. We have the main script here, network module, utils, AFL mutator, printing module, AFL mutator ported from C to Python, Radamsa binary for Linux, configuration file. We can look into code. It's just straightforward Python code, nice and fancy here. I tried to make it as clean as possible to be able people to contribute. So we have also AFL ported from C to Python. We see a lot of different strategies from AFL. And we have a couple of folders. In Windows folder, we have folders for DBI and instrumentation libraries for 64 and 32 bits. And same for Linux. So you can just launch them and run against black box binaries. And if you look into command line option, it's again like any other fuzzer. You have to provide path with your files that you want to submit in your target output, number of parallel fuzzers, switch between dump or smart mode. You can provide path to configuration file with more options, and you can restore previous session. So if you look into configuration file, we can find much more options. So they should be provided in this file format. So just option name, space, equal value. We can enable dictionary for AFL strategy. So AFL will inject tokens. And we also can assign weights for AFL, so in Radamsa. For example, we can say that Radamsa should mutate 20% of our test cases and AFL 80%. Or we can enable our own fuzzing strategy just by specifying its name. For example, we can say example mutator should mutate 20% of our test cases. We can run this deterministic seed, we can print more information, we can disable this volatile path suppression algorithm that I showed previously. And to be able to start black box binaries fuzzing, you have to specify which DBI framework you want to use. So it's DynamoRio or Intel Pin. If it's DynamoRio, you have to provide DBI root where it's located, the launcher, then client, supplied with Manul. And you can also specify for Manul what kind of libraries you want to instrument along with your target binary. So this way you can include them in your code coverage. There is timeout. Also, these options, netconfig master, netconfig slave, can be used to spread Manul over network. You just need to specify port and IP address. You can run it in debug mode if you need more information. Synchronization between different fuzzing instances. And we have command line fuzzing as an experimental feature. Just in this case, Manul will send it over command line. And to be able to enable network fuzzing, we just need to specify IP and port, for example, and protocol. So, for example, instead of TCP or UDP, we want to fuzz it over TCP. And we can also ignore certain signals, for example, SIGA board, which is quite annoying if it would be considered as false positive. Okay, we can actually start it. So we just need to say where is my binary, input folder, then provide output folder. In this case, we are doing fuzzing against 7-zip, then number of parallel threads, like 20, for example, then pass to our main binary, like in AFL, and then command line, like options. And that's all. Then just enter. It will spin up a lot of instances. Each instance will perform its own mutations. Then you can see the dry run is finished. So it's running. We already identified a couple of crashes. And there are a lot of other useful information like coverage statistics, performance, executions per second, files in queue, timing, what kind of mode we are running, and strategy. Okay, so I guess we can stop it and move forward. Now let's discuss vulnerabilities that I managed to find with this tool. So Poplar is an open source library for rendering PDF documents, mostly used on Linux. Free software products like Events, LibreOffice, Inkscape, used by million users across the world, integrated this library for PDF documents handling. And Poplar participates in Google OSS-Fuzz program, which makes it much harder to identify new vulnerabilities in this target using AFL and libfuzzer, because Google already generated trillions of test cases. So we just don't have enough CPU power. Okay, so I decided to try the same seed corpus with 491 PDF files used by OSS-Fuzz and run the latest version of AFL and Manul for 24 hours with 78 parallel jobs. As you can see, on average, AFL was approximately 25% faster compared to Manul. But execution speed is not the key factor here. If you compare paths found by Manul and the AFL, we can clearly see that after 9 hours of running, Manul managed to outperform AFL and continue to discover new paths in the targets faster than AFL. And this was possible because of the improvements that I introduced in the second part of my talk. So our corpus parallelization plus volatile path suppression plus combination of two mutators gave us much better results despite of lower execution speed. And more importantly, Manul managed to discover 3 zero-day vulnerabilities and 5 non-security related bugs in Poplar, previously of course unknown for developers. So NIST assigned the following CVEs for these vulnerabilities from medium to critical severity rate, and let's actually discuss a couple of them. Okay, so the first bug is a heap overflow that exists in downsample raw box filter, which is called by downscale image in libcairo library. And this function is actually used to downscale GPX images that might exist in PDF objects. I don't want to go deep into technical details here. It's not important. All we need to know that we can use we can trigger heap overrun by controlling pixel coverage variable. I marked with red, and force this function to read out of heap chunk to variables A, R, G, and B. And at line 40, we can write these values to the destination buffer. To the best of my knowledge, I don't see a straightforward way to exploit it, but most likely we can use this approach, this vulnerability, to get some pointer leak out of this vulnerability. So, which might be very useful if you want to bypass SLR. Okay, the second bug is located in GPX stream init. This function doesn't have a check for negative values. So I highlighted in red where popular read booth size, which we can control, and call toUnsigned char function without actually checking size of booth size. So in this function, toUnsigned chars, initial size can be very large. So it makes possible to allocate a really large heap chunk of arbitrary size. We can use this bug as a second stage in House of Force heap metadata exploitation, where we need to allocate a large chunk to be able to force malloc return an arbitrary pointer, a pointer to arbitrary place in our target memory. Okay, the last bug is more dangerous. Here we control variable I that can be negative, which might cause an integer signless error and heap out of bound read controlled by an attacker. So if we can satisfy the first condition and avoid this really huge statement, basically what we can do, we can return an address to an arbitrary object in memory, which is already pretty scary. So the caller function will check if this object is not 0, and then call one of its methods, which is pretty straightforward way to get control over RIP. So I indicated in red, this is our function, get entry, and then we just call entry, get flag. And instead of get flag, we can place a pointer to any place, to any function that we want. The only problem here is to prepare this object in the right way and allocate it in the right place. But I believe it's very possible, so it's straightforward to exploit this vulnerability. Okay, moving forward. Zeek, formerly known as Bro IDS. It's the world's most powerful open source framework used by thousands of companies and institutions across the planet. There are a lot of very powerful plugins for Zeek, such as J3, designed to fingerprint SSL communications, which is a very powerful technique to detect suspicious encrypted connections, usually performed by malware to communicate with C2, or Rantim implant to communicate with C2, depending on who we're talking about. So this project even has its own conference called BroCon, which takes place in Arlington every October. So authors of Zeek is very aware of memory corruption issues and fuzzing technique in general, because even a simple denial of service is completely unacceptable for such type of security products. So the code quality is pretty high, I would say very high, and they have done multiple fuzzing campaigns in the past. So it was actually a serious challenge for Manul. Unfortunately, Zeek has a very complex initialization routine that usually takes up to 10 seconds to initialize and start traffic monitoring. And it was very early stage of Manul that it was like just a couple of Python scripts. So in this case, if your target takes like 10 seconds to initialize, it's completely unacceptable for fuzzer to wait for 10 seconds. Fortunately, they have done a couple of fuzzing campaigns in the past with libfuzzer. So I managed to find an example of how to avoid this long initialization routine. So all we need is to implement a special wrapper for each protocol we want to fuzz, and an example of such fuzzer for SSH protocol shown on the slide, along with other 10 protocols. So I ran both fuzzers for 24 hours with 70 parallel instances for each protocol and managed to find 3 previously unknown vulnerabilities, and IFL found 0 bugs. This is the list of vulnerabilities I found. 2 of them are located in Kerberos and the last one in IRC protocol implementation. So while for the most application memory leak is not a big deal, for Zeek it might cause a serious issue if memory is not freed in a packet processing function. So memory leak in this case is a memory allocated on the heap but never freed. In our case we have memory leak in the function shown on the slide at number 1. So each Kerberos packet will cause Zeek to allocate around 130 kilobytes of memory, which will never be free later in the code. And we need to send a lot of packets to force Zeek allocate a lot of memory on the machine, and finally cause deny of service. I was able to write a simple exploit, which usually takes around 7-8 hours to force Zeek allocate 50 gigabytes of memory, leading to crash. But sending a lot of packets is a bit boring, right? What about one packet that can cause a deny of service and stop network traffic analysis? Remember IRC protocol? A decade ago, it was a very popular way to communicate with people in IRC chats using ICQ. So the protocol is text-based and pretty simple. You have a numerical code for command, space, and then user string. For example, using command 353, which is numerical code for nick, then space, the name, will assign a nickname in IRC chat for you. But if we send this command without actual nickname, so the function part begin will return 0, and then part arrays will be called with this 0, which will finally obviously lead to null pointer dereference and segmentation fault. However, IRC protocol is not enabled by default, and we actually need something else. It's usually up to blue team to enable or disable monitoring of IRC. But the last bug in Kerberos protocol was a bit more complex. So I don't want to go deep into technical details of this problem. I actually don't quite understand it at this point, anyway. But it seems like there is an integer type mismatch in bitpack generated parser code and Zeek analyzer itself that potentially can cause unintentional paths in some situations to be executed, leading to null pointer dereference in the Kerberos protocol parser. And usually it happens like 90% of the time. So we just need to send our packets 3 times instead of 1. And let's see it in action. So we are on the Linux machine. We have 2 files. The first file is a Python script that will connect to Kerberos server, and it receives IP, port, and path to the file with malformed Kerberos packets. The second file contains actual data, so actual malformed Kerberos packet. And we have a virtual machine with Zeek. And just to make it simpler, our Kerberos server script is also placed on this virtual machine. So in this script, we have to specify IP, default Kerberos port, which is 88, and file that we want to use for response. So let's actually start it. And I will just need to specify where the script file that we want to answer. Then we can run Zeek itself. It's just, we have to specify a name, interface that we want to listen on, and this is our IP address. Basically, it's just like local IP address of our virtual machine. But again, this Kerberos server can be placed anywhere in the network. And now we can just run this client. We just need to specify IP address, port, and our packet. So it already sent, and we can see segmentation fault and like stop of network analysis. So this is a pretty straightforward way. Thank you. So this is really pretty straightforward way to disable traffic monitoring in the network and then communicate with malware, with C2, or do some red team engagement on top of this finding. And I managed to catch more bugs with Manul in other applications, such as an open source tool 7-zip, its Linux version P7-zip, in Archiver for Mac. But unfortunately, these bugs are still waiting to be patched by maintainer. For example, for P7-zip, last time he was online, it was in 2017. I hope he's fine. So again, these bugs are waiting to be patched. I am not going to disclose them today, but I will definitely publish a post about this in future when the maintainers will fix it. 2 of them allow remote arbitrary code execution. Of course, Manul is now in beta stage, right? There are a lot of functionality that wasn't tested deeply enough, such as anything related to network, any help contributions more than welcome here. What is very strongly required for now is AFL fork server to be able to speed up Manul and perform network fuzzing more efficiently. I also want to add Intel P trace on Linux and Windows. I believe that Manul can be even stronger with structure-aware fuzzing, so more mutation algorithms, again, is strongly required. And basically, on macOS, we have a lot of stuff to do. Despite of a lot of future work, Manul already demonstrated that it's a very efficient coverage-guided fuzzer that can catch bugs in really tough targets, already tested by top security researchers. And I already released like 15 minutes ago, it's already public. It's released under Apache 2.0 license, so you can already pull it from my GitHub account and find your own 0 days with this tool. So you can subscribe to my Twitter account, add me on LinkedIn. If you have any questions, you can catch me later at DEF CON after this talk, or PM me on Twitter. So thank you for your attention.